visualize the following. Okay. A car is traveling at an average velocity of 60 miles per hour for 30 minutes. Then at 75 miles per hour for another 60 minutes. Okay? So use the sketch to calculate the distance traveled over 90 minutes. Looks like it's raining. So if we want to visualize it, one way to do it is to draw the following sketch. Say that this is the time, and since I'm dealing with miles per hour, I'll set up the times to be measured in hours. And since we're looking at an hour and a half, so this will be 0.5, this will be 1, and this will be 1.5 hours. Okay, and over this period of time, the car first initially travels at 60. So let's say this is 30, this is 60, and this is 75. So 30, 60, and 90, and 75 is right in between. So for the first half an hour, the car is traveled at a speed of 60 miles per hour. And then for the next hour, the car is traveled at the speed of 75. Now, since distance equals rate multiplied by the time, the rate, the velocity really, v of t, is the rate, right? So what we see that I can say that the area of this, the first what you might call it, rectangle, D1 equals R1 times T1, and the area under of the second rectangle will be D2, and it's a product of R2 times T2. Okay? And of course, R1 is the vertical value of this rectangle. So we have this area present the one distance, and the area of the second present the distance traveled over the next 60 minutes. So the point of this exercise is, if the graph is a graph of velocity, which is, then the area under the graph represent the distance, right? So the total distance we calculate from here, d equals d1 plus d2, or r1 t1 plus r2 t2, and in numbers we are looking at 60 times 0.5 plus 75 times 1, and this will be total of 105 miles. The point of this exercise is to realize that the velocity, which is the derivative of the distance, is the graph. So the graph, which in this case will be two pieces of horizontal line, is the derivative of the area. Okay? What we'll see later on next week, that we say the area would be really the integral of the function, which in this case is the velocity. So the title of the topic is area and distances, and you can see that actually I could have written here area equal distance, because when we visualize the graph of velocity over time, then the area below the velocity represents the distance. Let me give you another example that will fortify this idea. Okay, in this example, we're looking at the velocity, let's say, of a go-kart, that we accelerate over the first 20 seconds from 0 to 10 meters per second. And then we go steady for at this velocity of 10 meters per second for another, let's say, 45 seconds. And we want to sketch the velocity versus time and find out what is the total area, distance traveled. Okay, so let's write the problem. Again, this is a go-kart. How many of you built a go-kart when they were young? I did. You built a go-kart? Oh, you rode a go-kart. Talking about building one. Take an engine, a motor for a lawnmower, put it on the frame. And, no? That was okay, velocity of a go-kart is changing. Is changing from, let's say, from 0 to 10 meters per second in 20 seconds. Okay? Then the go-kart continues at a steady rate continues. A steady rate of the same 10 meters per second for additional 45 seconds when the go-kart comes apart. Well, I don't write it here. Let's say it stopped. So we want to sketch the velocity versus time and calculate the distance, the total distance traveled. All right, so it's similar, except there is a little wrinkle here. The fact that we accelerate at the beginning. So what we need to assume that we have a constant acceleration. So this is, we are not told, but we take the liberty to assume so. And the picture is going to be like this. So we have a total of what? The first 20 seconds. Right, so we have 20, 40, 60, and then 45 after the 20, so this gives us 265. So let's say this is 20, 40, and 60. Okay. So let's say this is the high speed. So here's the velocity, v of t, measured in meter per second. This is the time t measured in second. And we go from 0 to 10 over 20 seconds. And then for the next 45, so we go all the way to 65 at the steady rate of 10 meter per second. So this is the sketch. So we have two pieces, again, two different parts. So the area under the slanted line, which is the velocity changing from 0 to 10 meter per second over a period of 20 seconds. So we have this area, and this area represents the first distance. So d1 equal, and this area is, let's say, 1/2 of the base times the height. So it will be 1/2 of 20 times 10. And then, so it will be 100 meter. And then we have d2, which is the rectangle that is made of a length of time which is 45 seconds and height of 10 meter per second. So it's 45 times 10 or 450 meters. So the total distance d equals 550 meters. Again, the relationship between the distance and the distance velocity and the area. We are looking at the area under the graph of the velocity. This is v as a function of t, right? Which is really the derivative of the distance. So the curve or the line, the graph v of t is the derivative of the area. We can say the area is really the integral of the graph of the function. You see the relationship between, in this case, velocity, distance, and area.